something like this. So sort of a strange looking function. It seems to have kind of some sort of like ridges or something. Right? In certain directions the function is nice, in others it seems to have these ridges. Right? It's sort of odd, but let's calculate it along one of these paths, see what happens. So if we're given a path, right, we can use that path to evaluate the limit as a one-dimensional limit. Okay, so what we do is we take our path and we approach 0, 0 along that path. Here, notice that the numerator here is just always 0. So we've got 0 divided by some positive stuff. So in that direction of approach, at least, we get a limit. We get this limits to 0. Yes, question.
Where it says limit x, y approaches 0, 0. So should that be approaching t 0?
Aha, right, right, okay, yes. So the question was, should this limit really be approaching t0? What we want to know is, does this thing have a limit at the origin? Right? Does this limit exist at 0, 0? So we've got one nice path that goes to 0, 0. Which is this path. Right? So if we walk along the path t0, we approach 0, 0. Right, so what do? We take our path, plug it in here, see what we get, and it approaches something.
One more thing.
Sure, yep.
How, like, the first one are like really equal to each other, right? Like limit x, y approaches to 0, 0 equal to limit t.
Yeah, sure, sure. Right, so this is there should be like along this particular path. Yeah. If this limit exists, right, then it should go to 0 in every direction.
Why did you, as t goes to 0, I understand that part where you plugged in, but then why t goes to 0? It was like because of the specific case or something in the question?
Right, so for every value of t, this whole thing will evaluate to 0. Right, if I put in t equals 5.
No, like the limit as t goes to 0, the first one. Yeah, this one. This one.
Right, so this, yes, this, all of these questions are great, by the way. This path approaches 0, 0 as t goes to 0.
Oh, okay.
Right, so but there's many directions of approach, right? We could come at this origin from another direction. So now we'll see what happens along the path. So there's a bit of unwinding to do here. We have to figure out what the limit in t is. Right, so tt is going to 0, 0. So we'll have t approaches 0 again. So again, this is the limit along a particular path. We substitute in the equation for the path and we get here. And now this is something we can handle using first year calculus. L'Hopital, that kind of thing. All right, we can cancel a t squared everywhere. Now when t goes to 0, this guy will go away and we'll get 0 again. So along these two paths, we've got some good information. And along two paths, we know that the thing limits to 0. Questions there, thoughts there? Yes?
What if it's not approaching 0, 0, but two different numbers, like 5 and 10?
Right, yes, yeah. What if we're going to 5, 10 or something? We'll cover that case. Yeah, we'll talk about that because that's an important point. Essentially what you have to do is you have to modify your path. The limit not to t equals 0, but to t equals some other number. But yeah, we'll talk about that case. Yes?
It's just like approaching from the line y equals to x.
Yes. Yes, so the question was, is this approaching along y equals x? And it is. What's kind of remarkable is that this will actually go to 0 along any straight line. Okay? Bit of an exercise there, but along any straight line going to 0, this thing will 0 out. Now I want to show you a very clever choice of path. This is the kind of, sort of like some excitement. This is a hard choice to figure out, so I want you to see why I'm making this choice. Okay. We've been doing these limits as t goes to 0, and we know what happens when t goes to 0 of a function like this, right? We did polynomials divided by polynomials. We've seen a lot of this material in our first year courses. In what case do we get a non-zero number? Non-infinite non-zero number. Right, when would we get something like this limiting to a non-zero number? Maybe somewhere back. Maybe over here. Oh, yeah?
If there's an asymptote.
Yeah, if there's an asymptote, yeah, if we've got some kind of limit where these both go to, say, infinity, that would work, yeah? How else can we get a non-zero number if we're limiting to 0? What? Yeah?
Degree of like those policy.
Yes, right. Very, very, very good comment there. So we can get a non-zero number if these have the same degree. Okay, so I'm just going to note that down. We get non-zero if top and bottom have same degree. Okay, so far we've been using lines. If we use lines, we get cubic, quartic, right? We get different degrees. Now watch what happens if we pick a path that makes both degrees the same. Hello, welcome, come on in. Come on in, join us. I guess there was something I said. One of my favorite first class experiences was some, we were doing a calculus course, lots of limits, derivatives, talking about Newton and all this kind of stuff. And someone came in late, maybe 15 minutes late, just long enough. And they're sitting there, and then they come and they say, "Is this anthropology 100?" I was so tempted to say yes. But I was like, no, you're in Calc 1. Anyway. Imagine, though, if they would have thought about anthropology. Okay, sorry, so let's, now that we've completely lost our train of thought, what happens if we make the degree on the top and bottom the same? Okay, so makes the degree of the numerator equal to the degree of the denominator. Okay, this path will have some special behavior because it is a chance of giving us a non-zero number. Right, so so we notice that the degree here is 4. We want the degree here to be 4 as well. Right, so the degree of y is 4. We want the degree of x to be 4 as well. So we pick a very special path. Right? T gives us t to the 4. To get this to also be power 4, we pick t squared.
Just one.
And notice that here we get t squared gives us t to the 4. Okay? So when we take the limit along that path, we get here. So this is a very, very special choice of path, but it accounts for these ridges. When we look at our graph, we see that there's these kind of ridges that go up to some value. When we approach along the x-axis, we get 0. When we approach along the y-axis, we get 0. But there's a sort of like a parabola-shaped ridge. You know, it goes up. And if we approach along that path, we can get a non-zero answer. If we look at the contour plot, we can also see those parabolic paths going to 0. It's a very, very, very special choice of path. But it shows that these can all agree along straight lines and then disagree along a curved line. Okay, so that's a little bit about limits. We'll take a break there and then pick up at 4:15.